Welcome and thank you for your interest in LaMarche manufacturing and the A77 battery charger series. In this presentation, we will talk about the NERC requirements for substations and DC systems and cover how the A77 charger assists in compliance with those requirements. This topic is presented and discussed by Murad Dana, Vice President of Engineering and Marketing at LaMarche Manufacturing, and Richard Hutchins, LaMarche's electrical engineer and R&D engineering specialist. In this presentation, we will talk about NERC PRC-005-6. There are two parts that need to be covered and discussed regarding NERC requirements when it comes to substations and DC systems. One of them is PRC-005-6, and the other one is TPL-001-5, and that's what we're going to discuss in a later presentation, not in this one here in particular. In this presentation, as mentioned, we will focus on the 005-6, and we will go through the history and the requirements and how it applies to the installations in DC systems and substations. And we're going to also discuss how the A77 battery charger from LaMarche assists in compliance with those requirements. We're going to start the presentation by giving a brief introduction about the A77 battery charger and mention that this is LaMarche's SCR-based battery charger used in stationary applications. The main difference between this charger series and other battery charger series that LaMarche offers is the technology. This one is based on an SCR technology, while some other battery chargers are based on magnetic amplifiers, ferroresonant, or switch mode power supplies. This charger was built to comply with the industrial specifications for battery chargers. It was originally built to comply with NEMA PE5 standard, and then later on, as new standards have been in development, along the side of NEMA PE5, such as IEEE P2405, the A77DE does comply with the industrial battery chargers. This charger was built to work in multiple and different installations. So for that reason, we've made it with the flexibility to configure the charger with different AC voltages for the input and different DC voltages for the output. The outputs are offered to operate in a 24-volt DC system, 48-volt, 130, and also in 260-volt DC systems. The charger is offered in either a single phase or a three-phase inputs. And since this charger complies with the industrial battery chargers requirements, the filtering level in this charger is actually offered in two levels, either a battery eliminator or a level 2 if you reference IEEE P2405, or it's a filtered battery charger, or a level 1 if you reference the IEEE P2405 in regards to filtering in the output, where it drops for level 2, it drops the output of the lower DC voltages to less than 30 millivolts, or for the higher ones to less than 100 millivolts with or without a battery connected. The charger was designed and built to comply with many industrial specifications such as UL 1012 and other IEEE and IEC standards, as the charger was tested at third-party laboratories to make sure that it does comply with all the different standards that we are showing on the screen. The main thing we're going to focus on in this presentation is to talk about how this charger assists with the NERC PRC-005 and TPL-001 compliance. For the reasons that I have mentioned before about the flexibility and the standards that this charger complies with, it actually allowed us to be able to install this charger in multiple locations, many different applications, whether it's related to transmission and distribution, or it's related to power generation, if it's onshore or offshore applications. The flexibility to configure and add or remove features from this charger allowed us to be able to fit all those different applications and sites. Main things I'm going to mention about the A77 battery charger, and we're not going to go into the details of all the features in the charger itself. We're only going to cover the main ones that assist in the NERC requirement compliance. So the main thing about this charger, that it does provide a lot of monitoring for both the AC side and the DC side in the battery charger. along with monitoring the battery itself. So for the AC side, it monitors the voltages and the currents, and it has a capability to monitor the voltage and the current for each phase individually in a 3-phase configuration and provides alarms accordingly. For the DC side, it monitors the voltages, the currents, it monitors any ground alarms or faults that could happen and would provide alarms accordingly. For the battery, it has a capability to monitor the voltage of the battery remotely, monitor the hydrogen level in the battery room, the electrolyte levels of the batteries, and the battery temperature. And one of the newest and latest additions to the A77 Charger series that it has a capability to monitor the battery float current and the battery charging and discharging current. We're going to discuss all of these features later on as we go through the requirements of the NERC PRC. But one of the main things is not only monitoring these parameters, but it's also recording and reporting these the data that's being collected. So with the A77, it reports the data, whether it's on the LCD display or the LEDs, and it also has some additional features such as built-in data logging capabilities and the capability to remotely access the charger or access the data on the charger, whether it's through one of the SCADA protocols or through the dry alarm contacts. With that, we're going to start talking about the PRC requirements and how that affects the substations and DC systems and how the A77 assists in that compliance.
So really the purpose of PRC-005 is to ensure the reliability of the grid with maintenance and testing of components that are critical to the BES transmission and generation protection systems. Essentially, this series of standards was ultimately created from the Great Blackout of 2003. This was the largest blackout in US history. It affected over 50 million people, spread over 9,000 square miles. Over 2 days, this incurred a $6 billion cost and contributed to 11 deaths. Over the period of those 2 days, it wasn't even so much a problem that the grid had failed. It was really a problem that the grid had failed to restart. So from that, FERC decided to have a task force and create a report on what was the cause of the blackout and ultimately the failure to restart. Essentially, the failure to restart the grid was due to failure of critical components. And those critical components had failed, and they established it was really due to lack of testing and maintenance. Early testing could have identified these components as towards their end of life, and this whole situation could have been avoided. So from the task force, several reliability standards were produced. PRC-005-2 being the first of them to link the DC supply with including batteries and chargers. Since then, PRC-5-2 has been replaced by the -3, -4.5, and ultimately 6. These standards apply to not all stations, but they do apply to systems that are on the bulk electric system. You can view a several-page definition within the NERC glossary, but essentially it comes out to greater than 1,000 kilovolts of transmission. Take a look at this diagram. The blue section in the middle shows the transmission system, which is in between the generating and ultimately the step-down substations and the customer. When the transmission voltage is at 100 kV or higher, essentially this is what applies to a bulk electric system. The complete definition of what a BES is actually within this document, the bulk electric system definition reference document. This is over 98 pages. But essentially the gist of it is if you're transmitting at 100 kV or higher, you're on the BES. Within PRC-005-6, there are different maintenance tables that come up depending on the type of battery that you're using. In this case, a vented lead acid battery is on table 14A. This specifically, this maintenance table specifically refers to batteries not having monitoring attributes. So essentially at 4 months, someone would have to go visit this site to monitor the station supply voltage, the electrolyte level, and check for unintentional grounds. 18 calendar months later, you'd be coming back to, again, look at the float voltage, check battery continuity, connection resistance, etc. Even at the 18 calendar month or really 6-year interval, you're essentially performing a battery performance test. So not having monitoring is a heavy penalty because you have to visit the site so many times. This averages to almost 4 visits a year. The advanced features of the A77 can reduce your maintenance costs. A similar table, 1.4b. This refers to valve-regulated lead-acid batteries. So very similar to the previous slide in that we're discussing battery systems not having monitoring attributes, but at 4 months, we have to do the same. We have to verify voltage, look for unintentional grounds. VRLA adds another step where every 6 months you have to perform an ohmic on individual units. So for VRLA, you have even more truck rolls per year. Well, the A77 can reduce your maintenance cost. I've put this table together to essentially compare the vented lead acid and valve regulated lead acid maintenance schedules. At 4 months, you're checking voltage and unintentional grounds. And ultimately, these tables are pretty similar, but there are some slight differences. The slight differences really falling in, not having an electrolyte level to check on VRLA, or individual ohmics on the VRLA do not apply to the VLA. But ultimately, the technological challenges are very similar. We have to evaluate for voltage, grounds, float current continuity, and ohmic measurements. This time that's spent recording this is really not even the maintenance data that's being done. It's just recording the data. Full documentation system is required for the NERC auditor and NERC compliance. Ultimately, you must be able to demonstrate to the auditor that this work has been done at the prescribed maintenance intervals. So this involves several visits per year and several person hours that are not available for other tasks to be done. Not only that, this doesn't even mention how many hours are spent recording this data in a database to be able to verify to an auditor that the work has been done. So manual checks are very expensive to do. So how does the A77 actually reduce your compliance cost to PRC-5? Well, let's look at the visits. For valve regulated, ultimately you're doing roughly 11 visits per year. In VRLA, you're doing 15 visits over 3 years. PRC-5-6 allows for reduced testing and maintenance for points observed with a monitor. The A77 can also monitor your DC system. And with less visits, your PRC-5 costs can be reduced. Let's take a look at the maintenance exclusions table. It would be table 14F in the PRC-5 standard. So table 14F, for items that with component attributes that are being monitored on the left, no periodic maintenance is specified. What we've done for convenience is we've labeled all 8 of these attributes with a number for discussion. And we're going to discuss each of these in detail, and specifically how the A77 can reduce most of your PRC-5 maintenance costs. Let's look at attribute 1 and 4. Attribute 1 is high and low voltage monitoring, and 4 is float voltage monitoring. Well, the A77 monitors for the DC voltage. Let's take a look at what is the voltage now. You can tell what it is on the screen, and you can observe any alarm indications directly on the discrete LED indications. But that only explains what is it now. How about where has it been? So for high-low monitoring, And the float voltage monitoring, we also have built-in data log and trending in the charger itself. We record the data locally on a micro SD card. It's a very basic text file. It's a mixture of periodic and an event-based data log. So by doing that, we have a time date stamp of what the voltage is or was at that period of time, the current, the temperatures, input voltages, the ground detection. We can look at ground leakage. But what's important about that too is not only a periodic log that tells you what it was, but it also tells you when a failure occurs and when an alarm clears. So by having a mixture of periodic and an event-based data logger, you can tell what was happening on the DC system before the alarm had actually occurred, and you also have a time date stamp telling you when an event has cleared. This is fantastic for helping to eliminate intermittent problems. For immediate annunciation that the voltage is out of spec, we have configurable Form C relay contacts. The Form C relay contacts are on the A77 are fully programmable. The standard configuration that ships out of the building includes these alarms. Our time delays are programmable, but also we can program them to be latching or non-latching alarms. We can assign the relay functions and have different unique functions with them. Also, the A77 can provide remote real-time monitoring over SCADA. With A77, you can automate your NERC documentation compliance. We can talk over DNP3, over Modbus, over IEC 61850, or SNMP. The A77 is compatible with any SCADA system. Essentially, we can talk over serial or Ethernet via TCP/IP, or we even have direct-to-fiber options available. Within our SCADA, we have over 129 analog I/O points, including DC voltage, current, AC voltage and current on a per-phase basis, and ground leakage current monitoring. We also have the ability to remotely and in real time log the float current and the battery voltage and temperature. In addition to the 129 analog I/O points that can be remotely monitored, we can also see 111 different digital I/O points. Something that's very important about this is because you're using it at a BES site, it's important to have NERC cybersecurity in mind. We've actually put the A77 through a third-party NERC SIP cyber penetration test and passed with flying colors, allowing us to be spec'd into systems that are on the BES. So PRC-5 also has an exclusion. Let's look at point number 2, specifically for electrolyte level monitoring. So the A77 can become a central point in data collection. The A77 will connect to different third-party monitors. You'll see different brands that are available there. By integrating the electrolyte monitoring with the A77, we can have smart features, such as locking out the equalize, and this can reduce additional electrolyte loss. The electrolyte level monitors by themselves typically have dry form C contacts that could be monitored at an RTU, but by including it in the A77, you gain additional features and intelligence in your DC system. For example, if you had a low electrolyte level, not only are you telling the charger to bump out of equalize, but you're also writing a time date stamp on the data log file, and you're also telling somebody who's monitoring the system via one of the SCADA protocols immediately when this event has occurred and when it may have cleared if you have a faulty or intermittent sensor. So by adding the electrolyte level sensor to the A77, you have you really extend the power of those sensors. Let's look at DC ground monitoring, point number 3. Well, the A77 also monitors for unintentional DC grounds. Within a standard DC system, normally at a substation, you'd have a floating DC system. And when there's an unintentional leakage path, it's necessary that the charger monitors for this. So on the standard A77, we can monitor for ground fault on both the positive or the negative, write a time date stamp when the alarm occurs or when the alarm clears. We can indicate via relay contacts that might be monitored by an RTU, as well as sending a message out over SCADA to a remote monitor. We also have availability for adjustable ground detection options, and this allows us to adjust the alarm trigger thresholds for the ground detection, as well as add in capabilities for remote real-time trending of actual leakage currents and the ground balance voltage. And all of these analog values are available over SCADA. You might be using a third-party application such as Pi Historian to be able to log and monitor these particular thresholds for the purpose of continuous real-time or condition-based monitoring. Next on the exclusions table is battery string continuity, point number 5. Well, the A77 already monitors for battery string continuity. We'll start out with the float voltage, and we'll apply a 1-minute test where the charger output drops to a lower yet safe operating voltage. This is above the end of discharge voltage on a typical battery system. But because the battery is in parallel with the load and the charger output, as the battery charger output drops, now it's going to take over the share of handling the load, which would be the station standing load during the 1-minute test time. So over this 1-minute period, if the battery voltage only falls to a short amount, we're going to pass that battery as being healthy. If it dips into the red zone, we're going to identify it as a check battery system. This could be something as simple as loose connection. This could be a loss of electrolyte. This could be an undercharged battery. There's a lot of things this could be, but we'll identify it for you. Now, on the off chance that the battery loses continuity, as in this last example, the battery voltage drops relatively quick, but it hits an asymptote at the safe operating voltage of the charger. And because this open battery scenario wasn't allowed to fall to 0 volts during the test, the charger kept the system up and running. Well, that's important that the charger prevented a drop of the station load. So the battery test could be adjusted for a periodic test between once a day to once every 60 days. And all of this information is available over the internal data log or remotely over SCADA. And this does qualify for NERC battery continuity tests. In addition to this, point number 7, we have to monitor for float current on the battery system. Well, the A77 and the FCM products do monitor for float current. Real-time and trending of float current is the ultimate indicator of battery continuity, the battery state of charge, and it can indicate the battery's state of health. This will meet the PRC-5 and the TPL-001-5 requirements for float current. Later on, you'll be able to see another presentation available for the LaMarche FCM, the float current monitor. Stick around for details on that presentation. Points 6 and 7 we've grouped together because they both refer to measuring the intercell and or terminal connection resistance of the battery, as well as the cell unit internal ohmic measurements. So the ohmic value of each cell and interconnect requires either a cell level battery monitoring system, which can be expensive and very extensive. Normally on a system like this, you'll see voltage probes on each cell of the battery, as well as possibly cells across the strap, the interconnection straps of the battery, in order to make measurements in situ. Another option for this could be accomplished by taking manual measurements, which could be less expensive. Taking the internal ohmic measurements is pretty infrequent. It's really only once every 18 months that's required. And the visits that are required, you have to be there at 18 months anyways to inspect the physical condition of the battery rack. So it kind of makes sense in this, for these particular points, to accomplish this with manual measurements. So let's compare the overall table for manually collected data versus A77 remote monitor data collection. So this table you've seen before. It's the same one that we presented that resulted in 11 visits in 3 years for a VLA and 15 visits in 3 years for a valve-regulated lead-acid battery. Well, the A77, when on VLA, the vented lead-acid, we could reduce that to 2 visits in 3 years. And that's because the 4-month interval is fully monitored. We monitor for the voltage. We monitor for the electrolyte level. We monitor for unintentional grounds. So we don't have a 4-month visit. The 6-month visit already wasn't there for a vented lead-acid battery. So at 18 months, yeah, we still recommend going back to do the cell and interconnection resistance, as you still have to check the physical condition of the battery rack anyways. So this results ultimately in 2 visits over 3 years on this battery system. Whereas the valve-regulated lead-acid, the 4-month interval is also fully monitored, but you have to return for ohmics only. This results in ultimately 6 visits in 3 years. So let's look at the return on investment. Manually collected data versus the A77. Really, the A77 can save you 8 visits over 3 years. For vented lead-acid, that's an 82% reduction. Or it can save you 9 visits over 3 years with valve-regulated lead-acid, and that's a 60% reduction in your total visits. This is just one station. Think if you had 10 stations. You'd be saving between 80 and 90 visits per year if you had 10 stations with an A77. So you should automate your NERC documentation with an A77 because it provides a substantial return on investment and long-term savings. By integrating the system level monitoring with an A77 Charger, you get a lesser price point than a standalone monitoring system, yet it's less expensive than 4 or 5 truck rolls per year. In part 2, we'll be discussing NERC TPL-001-5. We'll discuss what it is. Does it really mandate redundancy or monitoring? When does the TPL-001-5 become effective? How does TPL affect the DC system? And again, how can LaMarche assist in compliance? As an overview, TPL-001-5, its goal is to mitigate a delay or misoperation of fault clearing and the single point failure of non-redundant components in a protection system. Essentially, this breaks down into 2 parts. The study of single points of failure of a protection system that could affect the ability to clear faults. Think of that as the ability to operate switchgear. And you must also be able to handle planned maintenance outages and run a stability analysis with spare equipment strategies. Think of LaMarche manufacturing, the powerful advantage.
Well, thank you, Richard. That was very good and useful information and details about the NERC compliance. And I know we did not give a lot of details about the TPL at the very end, but that will follow in another presentation. And we're going to go through pretty much the same thing, remind you of the main features of the A77, and give a brief description about the history of the NERC TPL-001 and what requirements comes with those standards. In the meantime, if you have any questions, please do not hesitate to contact LaMarche. You can contact our general email at sales@lamarchemfg.com, or you can call us directly at 847-299-1188. You can speak with any of our application engineers in the sales department, or you can ask for one of us directly to have further discussions regarding the NERC requirements. Once again, thank you for your interest in LaMarche Manufacturing and the A77 battery charger.